Welcome back to the deep dive. Today, we are unpacking something that, it feels like the definition of permanent.
Right.
When you want to say something will never change, you say it's as old as the hills, solid as a rock. We're talking about mountains.
The ultimate symbol of stillness. Or at least that's what we tell ourselves.
Exactly. But here is this mind-bending fact from the source material that just throws that whole idea out the window.
Oh, I think I know which one you mean.
The Himalayas are moving. They aren't just sitting there. They're alive. They're growing taller by about 5 centimeters every single year.
Which doesn't sound like a lot, but then you start doing the math on, a geological timescale.
Right.
And it completely changes how you see them. We look at a mountain and we see a finished thing, a statue. But really, it's more like a wave of rock that's constantly crashing upwards. We just don't live long enough to see the splash.
That is such a cool way to put it. A slow-motion wave of rock. And that's really our mission for this deep dive. We want to go way beyond just, Everest is tall. We're going to dig into the violent mechanics of how they're built, the surprisingly tricky science of measuring them, and then, of course, the human obsession with climbing them, the whole 7 Summits challenge.
And we're pulling all this from some really great documents, DK eyewitness records on Everest, geology, mountaineering history. And what's cool is they treat the mountain not just as a pile of rock, but as a living landform that makes its own weather, its own biology. It's a whole ecosystem.
I have to say, I was scrolling through and saw a comparison to a mountain on Mars that totally broke my brain. We'll get to that.
Oh, yes.
But I want to start with their birth. You used the word violent. And that seems right because building the Himalayas wasn't exactly a gentle process, was it?
Not even close. It was, and I mean it still is, a collision on an absolutely epic scale. To get why Everest is there, you have to rewind about 50 million years.
Okay.
The map of the world looked completely different. India wasn't attached to Asia at all.
Right. It was just its own continent kind of floating around.
Exactly. It was a massive island on its own tectonic plate, and it was moving north across the ocean at what geologically was just reckless speed, like 15 to 20 centimeters a year.
That's incredibly fast for a continent.
Yeah.
So India is just speeding up the highway of the Earth's crust.
You could say that. And inevitably, it crashed right into Asia.
And that's the key. Usually when plates collide, one slides under the other.
Right, that's subduction. The heavier one sinks. But here you had 2 huge, buoyant land masses. Neither of them wanted to sink. They were too light, so the rock had nowhere to go but up.
Okay, I like the car crash analogy for this. It's hard to picture rock folding like a rug, but if you think of a head-on collision,
Yeah.
the hoods of the cars, they don't just vanish. They crumple. They buckle upwards. That crumpled metal, that's the mountain range.
That's a perfect analogy. The hood of India is still crumpling against the hood of Asia. And here's the detail from the sources that just gets me every time.
What's that?
Because that area used to be an ocean floor before the crash, the rocks at the very summit of Everest, the highest point on the planet, are marine limestone.
Wait, hold on. So if you climb to the top of Everest, you're standing on what used to be the bottom of the sea.
That's it, exactly. There are fossils up there, sea creatures, trilobites, crinoids, all sitting at 29,000 feet. That's the power of this collision. It literally took the seabed and shoved it into the stratosphere.
That is unbelievable. And the scary part is you said the crash isn't over. The engine is still running.
Still running. India is still pushing north. That pressure is what creates what geologists call fold mountains. The Earth is literally folding in on itself.
Fold mountains, that's one type. But there are other ways mountains get built, right? It's not always a head-on crash.
Correct. Fold mountains are from that compression, the crumpling.
Yeah.
But then you have volcanic mountains.
Like Mount Fuji.
Or Kilimanjaro, yeah. That's lava and ash piling up from deep inside the Earth. It's material being added on top of the crust, not the crust itself buckling.
So a fold mountain is a car crash. A volcano is more like a leaky pipe that keeps building up a mound of ice.
That's a good way to think of it. It's coming from the inside out. And then there's a third type mentioned in the text, block fault mountains.
This one was a bit harder for me to get my head around.
Think of the Earth's crust like a giant, thick chocolate bar. If you try to bend it, it doesn't fold, it cracks.
Okay.
Those cracks are faults. And huge blocks of the Earth can get pushed up or dropped down between those faults. The Sierra Nevada range in California is a classic example. A massive slab of rock just tilted upwards.
Less like a rug, more like tilting huge paving stones.
Precisely.
Speaking of cracking, there was this photo in the source material that really drove home the side effects of all this. It was a collapsed freeway in Los Angeles from '94.
Right. And it's in there because it shows the cost of living on a restless planet. The same forces that push the mountains up, that grinding of the plates, they have to release that energy. The rock bends and bends until it snaps.
And that snap is an earthquake.
Exactly. The Himalayas aren't just growing, they're shaking. The seismic violence is the engine of their growth. It's a beautiful catastrophe.
The beautiful catastrophe. I like that. Here's something else that I found really interesting, this kind of paradox in geology. We tend to think older is bigger, more impressive, but with mountains, the text says it's the opposite.
The paradox of height. It's a fundamental rule. The highest mountains are almost always the youngest.
So the Himalayas, the biggest on Earth, are basically just teenagers.
They're the rowdy, jagged teenagers, yeah. See, as soon as a mountain rises, the planet starts trying to tear it down. Wind, rain, ice.
Erosion.
Erosion. A great comparison is the Appalachian Mountains in the U.S. They formed about 250 million years ago. Geologists think they were once as tall as the Himalayas are today.
Really, the Appalachians, I mean, they're beautiful, but they're so gentle.
They're gentle now. They've had 250 million years of being ground down. They're the old men of the mountain world. All their sharp edges have been worn smooth.
So what this means for you listening is if you see a really sharp, jagged peak, you're not looking at something ancient.
Yep. You're looking at the new kid on the block. Sharpness equals youth in geology.
Okay, let's talk about the big one. The sharpest, highest teenager of them all, Everest. 29,029 feet. But I love that the sources focus on the names because Everest is just, well, it's a bit boring, isn't it?
It's very administrative. It's named for Sir George Everest, a surveyor general of India. And he didn't even want it named after him. He thought local names should be used.
And the local names are so much better.
So much more poetic. In Tibetan, it's Chomolungma, goddess mother of the world.
Wow.
And in Nepal, it's Sagarmatha, goddess of the sky. These names show reverence. The British surveyors just called it Peak XV.
Peak XV just doesn't quite have the same ring to it. But here's where my elementary school geography class lied to me. Everest is the tallest, period. But the source material has some serious gotcha facts.
Well, tallest all depends on where you start measuring from, right? From sea level, yeah, Everest is king, no question. But if you measure from the base of the mountain to its summit...
The champion is in Hawaii.
Mauna Kea. It's a dormant volcano. From the beach, it's about 13,800 feet up, but most of the mountain is underwater.
So it's like an iceberg.
Exactly like an iceberg. If you could drain the Pacific and measure from its true base on the ocean floor, it's 31,988 feet tall, almost 3,000 feet taller than Everest.
That is wild. But even Mauna Kea is tiny compared to what's on Mars.
Yeah.
This is the fact I was talking about. Olympus Mons.
The undisputed champion of the solar system. I mean, Everest is, 8.8 kilometers high? Olympus Mons is 27 kilometers high.
17 miles straight up. 3 times the height of Everest. I can't even visualize that.
It's almost impossible. The base of it would cover the entire state of Arizona. And the detail in the notes that got me was the crater at the top, the caldera.
The mouth of the volcano.
Right. That crater alone is big enough to swallow the entire island of Manhattan.
How is that even possible? Why can Mars grow mountains that big and Earth can't?
It's those tectonic plates again. Mars doesn't have them in the same way. On Earth, the plates move, so a volcano gets carried off its lava source, its hotspot, it can't keep growing.
Oh.
On Mars, the crust just sat still, so the volcano could just keep erupting in the same spot for millions of years. And, lower gravity helps too.
So back on Earth, how did they even figure out how tall Everest was? Before GPS, I mean. They didn't even climb it.
No, they couldn't get near it. Nepal was closed to foreigners. It was all done with trigonometry, using these instruments called theodolites.
Theodolites. Sounds like a dinosaur.
It does. It's basically a really precise telescope on a tripod. They set them up hundreds of miles away in India, measured the angle to the summit, and then used high school math to calculate the height.
It sounds simple, but I imagine it was a nightmare.
Oh, it took decades. But they were incredibly accurate. Their final number was 29,002 feet. They were only off by 27 feet.
That's amazing for the 1850s. Okay, so there's measuring the rock, but there's also measuring the air. There's a great story about Blaise Pascal.
Yes, back in 1648. He wanted to prove that air has weight and that it gets thinner as you go up. So he had his brother-in-law carry a tube of mercury up a mountain in France.
And what happened?
As he went up, the column of mercury dropped. It proved the air at the top was lighter, less dense. The weight of the atmosphere was less.
And that's the thing that kills you on Everest, isn't it? It's not just the cold, it's the lack of air.
It is the critical factor. At 18,000 feet, which is just base camp, the air pressure is half of what it is at sea level. So your lungs have to work twice as hard to get the same amount of oxygen. And by the time you reach the death zone, above 26,000 feet, your body is effectively dying. It can't adapt. You're suffocating.
Which makes it all the more crazy that people decide to climb it. And not just it, but the highest one on every single continent.
Yeah.
Let's talk about the 7 summits.
The 7 Summits is this fascinating modern challenge, but it actually started a huge argument in the climbing world.
Right, the which mountain counts debate.
Yeah.
But first, the pioneer, Dick Bass. He wasn't your typical mountaineer.
Not at all. He was a Texas oil tycoon, a wealthy amateur in his 50s who just set this goal for himself. He hired the best guides, and on April 30th, 1985, he stood on top of Everest and completed the list.
And that kind of launched the whole commercial guiding industry we have now.
It completely changed the game. But then, a year later, along comes Pat Morrow, a Canadian photojournalist, and he says, "Congrats, Dick, but I think you climbed the wrong mountain."
This is the famous Kosciuszko versus Karstens thing.
Exactly. It's about how you define the continent. If you just look at the landmass of Australia, the highest point is Mount Kosciuszko.
Which the source calls a hill that provides no real challenge.
It's a walk-up. You could do it in sneakers. Pat Morrow said that violates the spirit of the challenge. He argued you should look at the whole tectonic plate of Oceania.
Which brings in Karstens Pyramid.
In New Guinea. And Karstens is a whole different beast.
The description makes it sound like something out of Indiana Jones. A limestone spike in the middle of a rainforest.
It is. You need actual rock climbing skills. Ropes, harnesses. So for serious climbers, the list with Karstens is the real one. It separates the tourists from the mountaineers.
Let's do a quick tour of the others. North America, Denali, or Met McKinley?
The coldest. It's just below the Arctic Circle. Ferocious weather, tons of avalanches. A really serious, dangerous mountain.
South America. Aconcagua.
The White Sentinel. Highest peak outside of Asia. It's not super technical, but it's a brutal endurance test because of the altitude and the insane winds.
And Europe. I always thought it was Mont Blanc.
That's a common mistake. Mont Blanc is the highest in the Alps. But the highest in the continent of Europe is actually Mount Elbrus in Russia.
And it's a volcano, right?
A twin-headed, extinct volcano, nearly 3,000 feet taller than Mont Blanc.
And finally, Africa. Kilimanjaro.
Another volcano, but this one's near the equator. So you're hiking through a hot savanna, and then the summit is covered in glaciers. It's this incredible contradiction.
Though the notes say those glaciers are shrinking fast.
They are. It's a fragile icon.
You mentioned glaciers, and that's the perfect transition. We talked about how mountains are built by this incredible violence, but they're also destroyed by it.
The great geological cycle. As soon as it rises, it starts getting torn down. And the most powerful tool for that is the glacier.
The source calls them slow rivers of ice, which sounds kind of gentle.
It's anything but. They're massive, they're heavy, and gravity is pulling them downhill. They act like giant sheets of sandpaper, ripping rocks out of the ground and carving the mountain as they go.
So they create those U-shaped valleys.
They scoop them out. A single glacier can move millions of tons of rock a year. The piles of debris they leave behind are called moraines.
But the most terrifying part, for climbers anyway, is the icefall. The Khumbu icefall on Everest.
It's the nightmare of every Everest climber. Imagine a frozen waterfall. As the glacier moves over a steep cliff, the ice can't bend, so it just shatters.
Into what?
Into deep crevasses and these huge, towering blocks of ice called seracs. Blocks the size of houses or apartment buildings.
It's all moving.
Constantly moving. These blocks can tilt, shift, and just collapse without any warning.
Yeah.
Climbing through it is like navigating a maze that's actively trying to kill you. It's the mountain grinding itself apart.
It's humbling. So let's recap this whole journey.
Yeah.
We started with the Indian plates smashing into Asia, crumpling the Earth's crust to make the Himalayas.
We learned the sharpest peaks are the youngest ones, the teenagers. And we looked at how we measure them, only to find out Mauna Kea is taller, and Olympus Mons on Mars just blows everything away.
We toured the 7 summits, debated whether a walk in Australia counts.
It doesn't.
And then we finished with the glaciers, these rivers of ice that are relentlessly grinding these giants back down to nothing.
It just shows you that a mountain isn't a thing, it's a process. It's a geological event that's still happening.
It's a battleground between uplift and erosion. It really changes how you look at them.
Absolutely.
So here's the final thought I want to leave you with. We know the Himalayas are growing 5 centimeters a year, but erosion is also tearing them down constantly. So it makes you wonder, are we looking at Everest at its maximum possible height? Or is it still just a baby? In another million years, could it be 40,000 feet tall? Or is there a limit to how high a mountain on Earth can get before it just collapses under its own weight?
That's a question geologists are still debating. Gravity eventually wins, but we might not have seen the peak of the peak just yet.
Something to think about next time you're looking up. Thanks for listening to this deep dive.
Keep looking up.
See you next time.